Hello and welcome to the Plus podcast. I'm Rachel Thomas.
And I'm Marianne Freiberger. The lovely music you just heard was mathematician Jürgen Richter-Gebert playing the exhibit he created for La La Lab. That's an exhibition produced by the group Imaginary. The show opened last September as part of the 2019 Heidelberg Laureate Forum, and we were lucky enough to visit the exhibition when it was filled with visitors, playing with all the fascinating interactive exhibits.
People often talk about the links between maths and music, though if you're neither a mathematician nor a musician, these links might not be so obvious to you. In this podcast, we'll have a closer look at maths and music by exploring the La La Lab exhibition with its curator Daniel Ramos. We'll ask Jürgen what links his work as a maths professor with his love of music, and we'll ask Andreas Matt from Imaginary to tell us how they want to invite us all into the playground of mathematics. And, as usual, we'll challenge ourselves to explain some maths in just 1 minute. But first, let's ask curator Daniel Ramos to show us around the La La Lab exhibition.
So I'm Daniel Ramos. I work for Imaginary and I am the curator of this exhibition of La La Lab. People think that mathematics and music are like water and oil and don't mix, because mathematics is a science, it's cold, it's exact, it's precise. And then music is about feelings, it's about expressing the human component. And I think it's one of the nice connections that visitors get here. And
so it's about showing that you can come here and have an experience of being a musician, but also an experience of being a mathematician.
And mostly you can have a nice experience if you're neither. So you can explore the exhibition just randomly, making a walk, or you can make like a logical path, saying, okay, start from the beginning. What do you need for making music?
What do you need for making music?
You need sound.
Yeah.
So what is sound? Sound is a perception of the human for a vibrating body, and then we are talking about acoustics and physics. So we have some exhibits here that show what is physically sound.
The sounds we hear are a result of vibrations of our eardrum stimulated by sound waves that are traveling through the air. And the pitch of the sound we hear is determined by the frequency of the sound waves. So the sound wave of a middle A on a tuning fork consists of just a single wave of frequency of 440 Hertz. Now mathematically, this is an example of a sine wave. But most sounds are more complicated and consist of many sine waves of different frequencies added together. And knowing the frequencies of these component waves is like having a fingerprint of the sound. Now, there's an amazing mathematical tool called Fourier analysis, which enables you to do just that, to get the fingerprint of any sound that you might hear. And this is not only useful for analyzing sound or for compressing sound, like the sound of this podcast, which will be compressed in an MP3 format. Fourier analysis is also useful, for example, for processing images, and these could be images of a medical scan or the photos that you see on your digital devices. You can find out more about Fourier analysis on plus.maths.org. But now let's return to Daniel, who is showing us how you can view the different pitch of notes as different frequencies on a spectrum, and how adding different combinations of these basic components gives you the sounds of different instruments.
And here we have this, for instance, this spectrogram that shows that what we hear on the ear, we can understand it mathematically as composed from several frequencies. And here we can explain all the theory, which is Fourier analysis for decomposing a sound. And we have here, in real time, we have a decomposition of the sound through the microphone to this spectrogram. We can have sounds which are more low or high in pitch, but you can also distinguish one instrument from another one. Mm-hmm. So even if I play the same note with a chord or with a xylophone, you can distinguish them. and the difference is on this spectrum, on this mixture of basic pieces. So in this case, there are sinusoidal waves. So for instance, here we can see that this instrument has this predominant frequency, and all the others are much
that
lower.
Was about 2,000 hertz-ish.
Mm-hmm.
Yep.
And on the other hand, we have string instruments that have much more.
So that sounds like the same sound, sounds like the same note, so but it doesn't look like the same note.
You can tune the string by the length and the tension, and then you can make it a higher pitch or lower pitch. But you will always recognize that it is a string and it's not a xylophone. And the difference is on this fingerprint, on this combination of basic components.
So the Fourier analysis of the sound essentially gives you a fingerprint of all the different frequencies that were used in making that sound.
Yeah, this is the thing that is essential to the instrument. You can tune it to make it higher or lower pitch, but you always have this fingerprint of this instrument created it.
So for example, in the stringed instrument, you had lots of frequencies adding into it, like the harmonics, but in the xylophone it was quite a pure.
It's quite concentrated.
Okay, so now that we know about sound and frequencies, let's go on to see how we make music out of sounds. So our tour of the Lala Lab moves on to Jürgen's exhibit, which is called Scale Lab.
And then that's essentially how do you create sound. But we are in a trip towards making music.
Yeah.
And here we have a keyboard and we have a line. And this line is continuous, and it represents all the possible pitches and frequencies that we can hear. So you can try to make music by playing any frequency, but you don't build instruments like this, and it's quite difficult to make music, because you don't use all the possible frequencies. You select some of them for making music. So here we have some of these points selected and connected to the keys.
Daniel's talking about the way that rather than using a continuous spectrum of frequencies of notes, when we make music, we pick particular points on the spectrum of frequencies to create a musical scale. And one of the things you can do in Scale Lab is choose which frequencies you want to associate with the keys on a keyboard, giving you the scales that you use to make music.
So these are the frequencies that we use for making music. But how do we choose these points? So what the ancient Greeks started exploring is what combinations of frequencies sound good. And then they found that, for instance, when you have one note and another which sounds at double the frequency, it sounds good together. And here you see that the quotient of the frequencies is a proportion 2:1.
Yep.
And it sounds so similar that they call it with the same name, and it's what we now call it's an octave of difference. They also found that this proportion of 3:2, 3 halves, is a nice proportion. And this is what it's called in music theory, it's a perfect fifth, which is a sound that it sounds good together. It is 3:2. And then you have this 5:4 and 4:3, which are the major and minor thirds, and all these intervals are nice. But for instance, if you see this quotient is 2:1, but if you go to the next one, 32:15, it sounds worse. So this is bad, this is good. So for Pythagoras and all these people that thought that everybody in the universe is numbers, they found that it's marvelous. So music is based on numbers, and nature likes small numbers.
So the Lala Lab exhibition sounds really amazing. It sounds like it really takes you through the maths and the science of music and allows you to play with it as well and to get creative. Now, the Scale Lab exhibit that we just heard from was created by Jürgen. And Rachel, I think you asked him to explain a little bit more about his love for mathematics and for music.
He was a really interesting person to meet. He was so passionate about both the mathematics and the music. And he told us how it is that he brings those two interests together.
So I'm Jürgen Richter-Gebert from Technical University of Munich, and I'm a professor for geometry and visualization.
And you developed this exhibit, and how is this related to your own background, your own work?
Okay, different answers to that question. So first of all, my major profession is being a professor for geometry and visualization. So having all these visualizations here comes out of this big stream of projects that we have doing visualization since 25 years or so. And so they are all built on our main visualization system, and which is somehow something for fast prototyping, interesting visualizations. That's one answer. The other answer, if I wouldn't have become a mathematician, I would have become a bar pianist or something like that. And I simply love music, and I love structures in music. And this was a great occasion to put all these different things together, to have things about rhythm generation, about the structure of composition, how music theory works together, and really going back down to the physical basics of how is sound composed, how does this have intercultural different things. So here at the Scale Lab you can also play with Indian raga scales or Balinesian gamelan scales, which are somehow based on a different idea of what is consonant, what is dissonant, but each of these things has some kind of a mathematical background, and we try to filter that out.
Unfortunately, none of us can visit the La La Lab exhibition right now in person, but thankfully you can visit it online, and you can play with Jürgen's Scale Lab exhibit at the Imaginary website, imaginary.org. Now, this openness and availability of the exhibits is one of the key principles of the work of Imaginary. It allows you or anyone else to recreate these exhibitions for themselves. So we asked Andreas Matt from Imaginary to tell us more.
I'm Andreas Matt. I'm Austrian mathematician, math communicator, human being, based in Berlin, and currently of Imaginary, a non-profit organization.
And what does Imaginary do?
We communicate current research of mathematics in an open way, an open, collaborative, participative way.
So you were saying in your talk today about this exhibition, La La Lab, that it was about giving people tools to kind of experiment with this mathematics and this connection with mathematics and music themselves.
Yeah. Working with tools for me, I don't know. I'm visiting a lot of museums and I'm seeing a lot of exhibits, and we have this criteria, which is very simple. So if the user of an exhibit can create something that surprises the author of the exhibit, then it's kind of an interesting exhibit. And I think as a user you would feel it's a little bit connected to school. You know, if I'm there and the teacher knows it already, I have just to learn it. There's no creative freedom. And maybe that's also the big difference between the school mathematics and the mathematics at university, that you have a lot of freedom. You have open questions. You're thrown into this nice open world of experimenting, of asking questions, of having problems and being challenged. And I think this creative challenge of I'm there and I can create something, I can invent something, I can be a mathematician in a way that I'm creative. And I think this type of exhibits work much better.
But the things you provide like leapfrog you closer to being able to do research, in that I can't play the piano, I can't play musical instruments, but the way that you've presented exhibits here gives me enough tools so that I can get to a point that I can then see how the mathematics is emerging from these things. So
yeah, Yeah, but it's also this kind of I can't somehow doesn't exist because it's all open. Even the authors of the exhibits or of the exhibition, even I don't understand the full exhibition because it's so deep, and it has so many open questions. So it's like the I can't becomes the challenge. Okay, I can't. Let's try. Let's discuss. Let's explore.
So we really encourage you to have a look at the La La Lab exhibition online at imaginary.org. It's really fun to play with the programs online. Another one, in addition to Scale Lab, that's really fun is called Tonics, which is a way of visualizing how the notes in a scale are laid out. So rather than thinking of the notes in a normal scale as a line, because the note bottom C of, say, the C major scale sounds the same as the top C, you can link those together and then you can think of playing a scale on a circle. And you can continue to do that, and you end up having things like having the notes that you could play laid out in a triangular grid, and then as you apply mathematical translations to the triangular grid, say sliding it across the plane, it's the equivalent of changing the key of a piece of music, or even reflecting the plane, you end up changing it from major key to minor key. It's so much fun to play with, and it's really surprising the stuff that you end up coming up with.
So in this bit of music that just played, which is the same one that played at the beginning, Jürgen created the melody in that music with his exhibit Scale Lab. But he also used another exhibit he developed called Beatbox to provide the rhythmic tabla accompaniment. And hidden behind the hypnotic beats of that tabla rhythm hides a very famous mathematical sequence, as curator Daniel Ramos explained.
Yeah, so this is essentially how many ways are there for making a rhythm with long and short steps. They say it's like how many ways can you climb the stairs, stepping once or twice each time.
The Beatbox exhibit is using 2 recorded sequences of tabla, one equivalent to 1 beat of music and one longer equivalent to 2 beats. And then it's trying to show you all the possible ways you could fill a bar of music with those 2 options.
So this is made with tabla, which is like a kind of drum that you play with your hands. And here, the short one it's a combination of it. It already contains several beats. But the idea is that you have a short piece and a long piece, and the long piece is the double of the short one.
If your pattern was only 1 beat long, you only have 1 pattern possible, the single beat of tabla. If you want a pattern of length 2 beats, you have 2 choices, either the single beat of tabla repeated twice per bar, or the double beat of tabla once per bar. To fill a 3 beat pattern, you can start with a single beat tabla, giving you 2 beats left to fill, which is back to the case of the 2 beat pattern. Or you could start with a double beat tabla, leaving you a single beat to fill, leaving you in the case of the 1 beat pattern.
If you have 4 beats, how many ways are there for putting 4 beats distributed in 1 and 2? Mm-hmm. Well, you can start with 1, or you can start with 2. Mm-hmm. And if you start with 1, you still have to fill 4. So you go back to the previous case.
The way you could fill up 3 beats.
You could fill 3 beats. If you start with a double beat that steps 2, then you still have 2 slots, and all the possibilities is 2 steps back. It's 2 iterations back.
So it's the number of possibilities for 2 plus the number of possibilities for 3, get you the number of possibility for 4, which is...
That's why you get the Fibonacci numbers.
the sequence of numbers from the tabular patterns in the beatbox exhibit is, of course, the famous Fibonacci sequence. Now, it's pretty unusual for a mathematical sequence to be famous outside of the maths community, but the Fibonacci sequence has made it big. It's quite famous. The first few numbers of the sequence are 1, 1, 2, 3, 5, 8, and then it continues forever. What defines the Fibonacci sequence is that at any point in the sequence, you get the next number by adding the previous two numbers in the sequence together. So, for example, the first two numbers are 1 and 1, add them together, you get 2, add together 1 and 2, you get 3, which is the next number along, and so on. So now we move to the maths in a minute part of our podcast, and I'm going to challenge Rachel to tell us as much as she can about the Fibonacci sequence in 1 minute. Ready? 1, 2, go.
Back in the 12th century, Leonardo Fibonacci was thinking about some really highly fictionalized rabbits. You start with a pair of baby rabbits, one male, one female, and they mate after 1 month, producing another pair of rabbits at the end of the second month. And then they'd keep on producing a pair of rabbits, a male and a female, at the end of every month from then on. So at the end of the first month, they mate, but you still only have one pair. At the end of the second month, they'd produce a new pair for the first time. So now you have 2 pairs. At the end of the third month, the original female would produce a new pair. So now you have 3 pairs. And at the end of the fourth month, the baby rabbits produced 2 months ago produced their first pair, while the original rabbits produce another pair. So now you have 5 pairs. Fibonacci wanted to know how many pairs of rabbits will there be in 1 year. Well, the total number of pairs this month is the number of adult pairs plus the number of baby pairs. And the number of adult pairs is the total number of pairs last month, including adults and babies. And the number of baby pairs this month is the number of adult pairs from 2 months ago, as it takes them at least 2 months to be old enough to produce babies. So the total number of pairs this month is the number of pairs last month plus the number of pairs the month before. We get the sequence 1 pair, 2 pairs, 3 pairs, 5 pairs, and so on, now known as the Fibonacci sequence, where each number is the sum of the previous 2 numbers in the sequence. And knowing the pattern of the sequence, you can work out that after 12 months there will be 144 pairs of rabbits.
Wow, that was great. That was almost all in 1 minute. Now, real rabbits obviously don't breed as Fibonacci described in his maths problem, but his sequence still appears frequently in nature, and it seems to capture some aspect of growth. You can find it, for example, in the turns of some natural spirals. You can find it in plants, for example, sunflowers, and even in the family tree of bees. The sequence is also closely related to a famous number called the golden ratio. You can find out more about Fibonacci on our website at plus.maths.org and search for Fibonacci.
This is the sound of the Fibonacci sequence as depicted in the Beatbox exhibit from La La Lab. After Daniel Ramos had revealed the Fibonacci hidden in the tabla patterns in this exhibit, we discovered that the music was also thanks to another brilliant mathematician. And I heard that this tabla playing is actually the Fields medalist Manjul Bhargava playing, that who's been sampled for these.
Yeah, that was his recording that was used for this exhibit.
So you can come and make music with the Fields medalist.
That's it for this Plus podcast. You can find out more about maths and music and about the Fibonacci sequence at plus.maths.org. And we leave you with Jürgen's wonderful music, performed with help of Fibonacci and, of course, the famous Fields medalist Manjul Bhargava. I'm Marianne Freiberger.
And I'm Rachel Thomas. Goodbye for now.